Hi friends, hope you are doing well. I'm Dr. Ganguly. Welcome to my channel. So today I'm going to discuss about incompressible flow and compressible flow, and specifically we are going to discuss what is the Mach number at which we can separate these two type of flows out. So at what Mach number should we use the incompressible flow equations, and at what Mach number should we use the compressible flow equation. So this is a very important topic. We have mentioned a couple of things before, such as 100 meter per second is the point and so on. But today we are going to actually show why this is so. And for that, we can use some of the isentropic flow relations which we have obtained in our previous classes. So let's go back to those relations and again look at a typical streamline which is in isentropic flow, which means that there is no heat coming in or going out from within this streamline, and also that it is frictionless. So let's assume that the values or property at point 1 are P1, rho 1, T1 and M1, and the values at point 0 are P0, rho 0, T0, M0. And so what has happened is that the flow has been brought to a standstill or a stop at this point 0. So essentially this is a condition which we have seen before. This is something which lets us calculate the total quantities which are P0, rho 0, T0 and so on. And obviously if we have brought the flow velocity to 0, the Mach number at that point is 0 because Mach number is velocity divided by speed of sound. So we saw that T0 by T1 could be obtained as this equation, and we could obtain rho 0 by rho 1 as this equation here, which is 1 plus gamma minus 1 by 2 m1 square by 1 by gamma minus 1, where gamma is of course 1.4 for air. Now, why this equation becomes important is that it's going to tell us something about compressibility. So remember, compressible means that can the air be compressed, and that would mean that density would change. So compressibility is directly tied to change in density. Recall that in the incompressible flow situations, we were assuming that density was constant, density did not change. So what we are going to do is we are going to reverse that thought process here. We can use the same equation, but we are saying that we are going to start with the velocity of 0 and we are going to speed up, and finally my velocity is going to end up as some v. So the Mach number is going to be m1 here. The Mach number is 0 at the starting point. So all I have done here is I have flipped the equation or the mindset which we had for total pressure, total density, total temperature calculation. So now again the same equation applies, except that rho 0 and rho 1 have changed the sides on this particular flow. So now we look at this equation, and what we are going to do is we are going to try to plot this equation in the next slide. So that's what I have done here. I have plotted the density ratio, which is rho 0 by rho 1, with the Mach number, and I have assumed the value of gamma is 1.4. So I get this curve here, and you can clearly see that at the point Mach number is 0, this is going to be 1 because this part is going to be 0, and then this curve typically goes up. So what this means is that as Mach number is growing up, the rho 0 by rho 1 ratio is becoming progressively larger, and only at m is 0 are they exactly same. So at that point you can certainly say the flow is completely incompressible. Now we can see that if we go to some Mach number like 0.3 here, where I have drawn this straight line, then the difference between the rho and the rho 1 value, or the rho 0 and the rho 1 value, is actually quite small. So the difference is only so much, and we'll see that this is less than 5%. So just to solidify that, I have put it in the table form. So essentially what I did is I put this equation in Excel and I plotted it. You can also do this for clarification. And so you will get something like this here. So at Mach number 0, the density ratio is simply 0. And as the Mach number goes up, the density ratio goes up. Now we can see that at 0.3 it is less than 5% because it's 1.045, 1.05 would be 5%. And of course, if you go to some Mach number like zero point 0.6, it's becoming almost 19%. That means there is a 19% change in density. Here there is a 5% change in density. So we could assume, if we do not want to use all the complicated compressibility things in our life, and we want to stick to the incompressible flow equations which are generally valid for low speed regimes, then below Mach number 0.3 I can consider the flow to be incompressible, and at Mach number more than 0.3 I can consider the flow to be compressible. So let's define this formally. At m is zero point 0.3, the density change is less than 5%. So we assume that the flow is incompressible here whenever Mach number is less than zero point 0.3. Now we know the speed of sound is 340.3 meter per second at standard sea level. So if we multiply this by zero point 0.3, we get the speed of sound, or we get the speed of the vehicle corresponding to Mach number zero point 0.3, and that would be 102.9 meter per second. So generally we can round this off to the lower value of 100 meter per second, and we can say that if the airspeed is below 100 meter per second, then the flow is incompressible flow. And so that is why we were making that assertion many times previously in this class, that whenever an airplane is flying below this flight speed, we can assume incompressible flow. Again, you can see it in the table here that below zero point 0.3, the changes would be something like 3%, 2%, 1%, 0.5%, and so on. And so this region, we can say that the incompressible flow assumption is correct. So we see that this equation, which was based on isentropic flow, has helped us get the point where Mach number changes for incompressible to compressible. So we see that density changes at speeds over m is zero point 0.3 or 100 meter per second. So that is the point of separation. And so we can say that flow is incompressible when Mach number is less than zero point 0.3 or velocity of the airplane is less than 100 meter per second. So you see many small planes which you see flying around, they are typically in this kind of regime. For example, planes which are used to train people, and also which people fly between two cities here and there for their own personal predilections. Then those planes are very small, they are typically low speed planes. But most of the planes actually fly at speeds which are greater than 100 meter per second. So whenever you are going in a very typical jet aircraft which takes you between two cities or between two continents, if you are going in international flights, you are certainly going to encounter this region of Mach is greater than zero point 0.3 and velocity is more than 100 meter per second. And in all those regions, you have to consider compressible flow. So this was the video for today. It is a important topic, and we have some idea about why the demarcation at Mach number 0.3 takes place. Very often in textbooks, this is just given as a fact you need to accept, but now you see that it is actually an assumption, but it is a pretty good one, because when you are below Mach number 0.3, there is very little change in the density of air between 2 points. So I'll end this video here. I will see you in a video sometime soon. See you then.